it's a lot easy because you can just move these viewports around, right? And yeah, and that's the picture looking at it from here, right? Okay, so we got some subterranean, like you see this 2 level, we are below grade, no more than 1, 2, 3, 4. So we're gonna have a retaining wall situation that we have to deal with and think how we're gonna build it, right? Not only that, as you excavate to go to that level below, you need to provide support, temporary support and shoring to the side of the building. So that's one of the things that you guys need to look into it. And then this sheet, that's a wall section, and that's our partial section, and that's important because it gives you more information as far as the height limitation. So from finished floor to finished floor, you getting old. Cannot see. Can somebody look at that dimension? It's 9 foot 5, right? You guys see that? See the dimension? Can you see it? Anybody has it?
Yeah.
I have a magnifier,
9 feet 8 inches.
9 feet 8.
Yeah.
Okay, so if we drop a beam, if we go with a beam and a slab, can I put a pen? Can I get a scratch paper? I want to scribble on this. Thank you. So the two systems that I was discussing earlier, the first one is just a flat slab like this. Then you have the column frame into it, right? The other system is you have a beam, like what you learned in the concrete, right? And then the column support the beam. So in a plan view, here you just have a big plate, and then you got the columns, right? Where in this one, you have a bunch of beams like this, right? The problem with this, if you look to the section, your clear ceiling height start from here, right? And usually the depth of this beam range from 24 to 36. So we'll eat up a lot of the space. You don't have that room, right? And the clue is looking at that elevation, especially if you have a height limitation from zoning or from planning. A lot of times cities have like certain ordinance and would tell you that maximum height because of aviation or whatever reason cannot be 110. And your goal as a developer is to, stick in as many floors as you can, right? So if you lose a couple feet every floor, you might end up just losing entire floor by the time you're done. So that's loss of revenue for the developer. So
we have to.
But that's cheaper though. That's a cheaper, system compared to that one. So
The slab would be thicker.
it's not thicker. I mean, this one you can do it with conventional reinforcement. You don't have to go to post tension. This one, to come up with a practical cross section, you have to go with post tension. So that can be conventional, just reinforced concrete. Okay? All right, so that's the gravity system. It looks like we're gonna settle into this one. So the question now, are we gonna do it cast in place or a precast? If we go with precast, we can use these planks that I showed to you. But you still need beams for the planks, and we don't have the room for that, right? So I don't think that will work either, all right? Unless we go. So, I mean, the more we study this, the more we're gonna learn. But you see the exercise I'm going through in using the process of elimination and finding why this would not work, why that should work, right? And these are the questions that you wanna be able to answer to the architect or to the developer, because they're gonna throw them at you. Why didn't you use this? I have that connection with, Bancrete, and they can do it cheaper, right? So you wanna be able to come up with, again, an answer to defend your decision. When you present the project, people from the industry will not challenge, but will try to examine your thinking process, and you wanna, again, as I said, you wanna explain to them that you went through all these different alternatives and you found out that this is the most viable solution considering the constraints. So we have like budget constraints, which is you want to do it the most cost effective way, and we have a site constraints. You are right next to that big cliff, right? And the crane that you guys mentioned, that's a constraint that will limit the use of the precast, plus the you know, the fact that we have that 9-foot clear height that we want to maintain, and we don't have any beams. Okay? Any questions? All right, so that's our gravity system. Post tension, slab, on reinforced concrete columns. Now, the location of the columns are given to you by the architect. The architect kind of, and usually early on in the process, the architect coordinate that with the structural engineer, during preliminary design. So if we go to some, sorry, can you? If we go to one of the, so this is again another detail sheet. This is a section now, and that gives very good information as well. You get the slab thickness, approximate size, the clear height for the subterranean parking, right? The volume level. There is room for some beams here if you need to, and then again the typical floor height. But I'm looking for, okay. So a section at the stairs that becomes handy when we design the stairs, so you know where you can put the landing. And as I'm looking at this, at grid line F, it looks like there's a big, massive shear wall. So this is section BP, section B, okay, at grid line F. I want to know what's going on here. So let's look at the floor plan and see what happened at section F. You see this massive? So, oh, here it is. Looks like there is a shear wall there, or an opportunity to have a shear wall.
Yeah.
You see that element?
Okay.
And it looks like, again, during the early stage of design, the engineer and the architect recognize that wall has to be fire rated, so we're hunting two birds with one stone. The concrete will provide the fire rated you know, capacity that's needed for that stair, and at the same time we'll use a shear wall. Also, I'm looking at the stair, at the elevator shaft, and I'm seeing these massive concrete wall. So again, the walls are serving dual purpose. They're providing their fire rated, and we can use them for shear wall, right? So here's our lateral system. Okay, we'll try first to see if the shear wall alone can carry the lateral load. If they don't, we can try something else. There is a system. Have you guys learned about dual system?
No.
Dual system is a shear wall and moment frame at the perimeters. So next time I meet with you, I'll go over all the different lateral resistance system. I'll have a PowerPoint presentation, and I'll go through them. But we're not gonna do that. We're not gonna go through the moment frame / shear wall unless we find out that the shear wall alone is not gonna do it. It could be a foundation constraint. It could be the amount of overturning that's going into the foundation is so huge that the soils will not take it without going into like crazy 200 feet cases. And then you say, no, that would not gonna work. I'll have to add the columns to it. But as I'm studying the plans, I was able to identify, right? And that's the exercise that I want you guys to go through when you. I was able to identify opportunity for the lateral, and let's go back to the floor plan, and for the gravity as well. So now we're moving from the park. These are the parking. So let me put this here. 820. So that's like the lowest level at the basement, B3, B2. So that's a level higher. Again, these are the parking stalls, right? B1, you still have the parking, you're still below, you're still here, right? B3, B2, B1, right? We are now at level 1. So what is level 1? We're right here now. We're here. A level 1. Okay, and it looks like this site is in a slope. So like in this elevation, you're at the street. But in the other one, watch. Level 1 is like 45 feet or 50 feet at the top. You guys picture this?
Yeah, I'm recording.
Oh, you're recording?
Yeah.
Okay. Should ask me, but that's fine. But you understand what I'm talking about? At this elevation, at the north elevation, level 1 is at grade. Let's bring south elevation. Oh, that's the west. Where's the south elevation?
So that one underneath there.
Yeah. Do you guys understand the difference? Look, where's the grade? This thick line represents the grade.
Okay.
That means the building is in a slope site like this.
Yeah.
So at the north, you're here. At the back, you're right there.
Got it.
And then the building. You understand now how it works?
Yeah.
Okay. All right. So again, let's go back and try to examine the plans. You got these columns, and again, they are very well thought out. So you probably that actually kind of have of your.
Which ones are columns? Is it all of the squares?
These are columns. Anything that when you cut and you hatch, that means that's a solid
Okay.
cross section. So that's a column.
Okay.
So these are columns. All right. And here is the level 2. So these are your columns. If you notice here, they are square or circle
Yeah.
for an architectural reason, I think. And here is an interesting feature. This section, this slab, is actually cantilever in and out of that column. So you have like so you need to go back now at that section 1, 8 to 7, and see what's going on in here.
Yeah.
1, 8 to 7. All I'm trying to do today is to show you how you read these plans, how you read
Okay.
blueprint. Okay, 8207. 8207. Is it 2 or 3? 3.
Yeah.
Okay, so what level is this? This is level 3. So we are here. Yeah, sure enough. Look,
Got it. So it's like white.
it's sticking out, but it's set into that grid line 1. No, is that 107? No, I'm not
It's
looking out
1.
correctly. It's 1. So actually, this is here, and there is a lot of column. So let's look what's going on at 7. Here is 7. There is level 1. So it looks like there is a terrace or a balcony.
Yeah.
You guys see that?
Yeah.
All right. So when you model it later on in the computer, you want to be able again to translate all this information accurately into the computer, right? The building is not, is not perfect square. It goes and it flare out as you go at that level 1. All right. It just caught my eye. So
What are your like? Oh, can you go back to? What's like the ones with this like that are not?
these are just architectural.
Oh,
They are
okay.
fins, and they are there to screen the sun
Oh, okay.
going into the window.
Gotcha.
Okay, because it looks like the sun is gonna hit the building that way. So they are. It's like Building 9. You see the old part of Building 9, even the new part of Building 9. You see these fins and the elevation. They are there to deflect the sun, direct sun, because the east, when the sun rises, it faces that elevation. So you want to prevent having a direct sun. Heat going through the glasses along that elevation of the building. So these are the columns. You see them?
Yeah.
All right. And now we're going to the typical floor. So now we are in level 3. We are right here. Now we are in the, the hotel room section, and this is the roof below. You see they're sloping the roof. These are floor drain.
Oh.
Okay, for the roof. And then this one is level 4. That's the typical. So you see that element is actually continued. That shaft goes all the way.
Yeah.
Right? You guys see that?
Yeah.
And again, here is the columns. Keep repeat itself. And these walls, I'm gonna have to assume they are non-structural partitions,
Yeah.
right? The only structural walls will be the one that you see heavily hatched. Yeah.
Okay.
Like this shear wall, that shear wall, this shear wall, and these two. And I'm just concerned with the fact that you have these two massive shear wall in that direction. The building is not going to be symmetric. I guess it could be because I'm going to let you exercise that. You want the center of the mass of the floor to coincide with the center of rigidity. You guys learned that in earthquake engineering, right?
No.
You know what center of mass and center of rigidity? No? Okay. So remind me to go over that with you. Basically, the building, the way I see it, for the first time, the number of the shear wall that we have in this direction, they're not symmetric. You got one wall here, there, here, and there, and they're not symmetric, right?
Yeah.
Correct?
Yeah.
But that could have been done for a reason, and we're gonna learn why they did it that way. Well, in this direction, because when you design for earthquake or wind, you have to have a capacity in each orthogonal direction. So you want to have a lateral capacity here in the north-south and east-west. The other thing that I notice, in the east-west, you have only this shear wall and that shear wall. And that makes me, and if you look to the length of these two elements, it's not the same length, right? So there's something else that they use. But if you notice, look at the column orientation.
Oh,
Yeah.
Girl.
So in that direction, they have this column oriented that way. So that frame, I have to believe it's working with these two shear wall, right?
Yeah.
Because it's the same mass. The building should be, equally stable in east, west, and north, south. But now I'm looking at it. So again, when we model this in the computer, well, same thing in here. Look.
Yeah.
Right. So the orientation of the column in a certain direction is done for a reason, right? That's the other thing. Again, the preliminary design for all those things likely in that project will be given to you. Okay. Again, typical floor. One thing here also you may notice that no, it's the same. I thought the length of that will shrink as you go up, but it does not. And that's the final roof. But the thickness of that wall is reduced as you go up. See how thin it is now when you're on the roof level? But it's thicker, okay, in the lower level. So what you need to do next, now we are able to conclude what system we're gonna use, is to come up with some material takeoff, like how much. First of all, you wanna know how thick is the slab that you need for the typical floor, for the roof, okay, and also for the parking. And who's taking concrete right now?
Okay.
You are. Who's teaching your concrete class?
HG Brown.
Fran? Okay, he's a big buddy of mine. When you study, but there is a criteria for deflection control, which is L over 200 or L over 180. Have you guys went over that in the one-way slab design?
I think Monday.
Okay, but you can check with him. If not, I'll help you. But usually there is a minimum slab thickness based on the span and the number of the span. So you can say, okay, well, here is my slab. Let's start with a typical floor level. We'll start with the roof. Okay. Start with that level. So it's not good here. So here is one. This is one line of support, right? You got that column, correct? Another line of support. So that's third, fourth, fifth. So the structural system, looking at it in this direction, is if you take 1 feet unit strip of that slab. I don't want to do this, but I have to now. I'm sorry, because that's what we do when we design. It's just 1 foot, right? The structural system of that, you have a uniform load from dead and live, and these are your support. at the column grids. You agree? And this is your W, right? Which is dead load, and there's W live load, correct? And this is your span right here. You're gonna get them from here.
Oh, the dimension.
Yep.
Okay.
And you're gonna have to have another 1 unit strip in here. Then come up with again with the support system. So you got line of column here, another line of column in there, right? Got that one here, correct? Got this one in here, and that one. Now, I mean this one, 19, 26, right? So, and you want to plot them. So if you look up for post tension, there is like a minimum slab thickness, and you can come to my office, I'll lend you a book that show you this requirement. So it's usually T is L over a number. I don't have on top of my head 180 or 240 or something like that, right? So L will be like, you want to look to the maximum span, so let's say 25. So 25 feet times 12, right? And you divide that with whatever number in the book. And that will be the minimum thickness that you have to have without calculation, just to maintain deflection, right? And that will be the thickness of the slab that you're gonna start with.
So we don't actually have to calculate deflections based on the dead and live load? This is
You will, but this is to narrow down your guess.
Okay, that's like a approximate.
It's
pretty
approximate because you have to maintain this,
good. Okay.
right? So this is your first, and then you do your analysis and everything, and then
And then if it turns out to be more,
then you go back. But instead of let's say the number that you need is 6 inches or 8 inches. So if you don't, and you plug it in here and it give you 5, right? So you do a correction in one line of creation, you're gonna get, you're gonna get back quickly to the right answer with 6 instead of like guessing 12 or 14, and then it's too much. Then you try 13, too much, 12, and you go through multiple iteration until you get the correct answer. But when you use this criteria, it gets you to the right answer very quick, and more than likely this one will control. Okay, and then you start with a slab thickness, and then you use the reinforcement and the post tension to carry the strength that you need for the slab. Okay. What else was going to say? So look into this, and so I want you to do that, and I want you also to, once you do that, you can come up with a load criteria. So I want you to calculate the dead load, and the dead load, you have a dead load for roof, and for typical floor, and the basement slab, because you have 3 different slab system, right? So it will be, for dead load, will be the slab self-weight, okay? And again, you take like a typical foot by foot, slab, and because the number that you're gonna have here is gonna be in pound per square foot, right? So let's say you go with 6 inches, just hypothetically. So it'll be 6 over 12 times 150.
It's like a spider.
Oh,
It's getting like.
oh, very close. Oh, thank you. So it will be 75 pound per square foot. That's the weight of the slab, right? Then you have partitions. And we're gonna assume it's like 10 pound per square foot, right? For these partitions. Then you have mechanical for the duct, and then you're gonna assume a number for that, maybe 15 pound per square foot, right? Then you have flooring. So I don't know what you have. Is that carpet, tile, right? You're gonna have to guess a number. I already give you, right?
Yeah.
Yeah.
Quite a bit.
Is
And
that
then,
also in the ASCE like?
right,
Yeah.
it's in the SE book and it's in the Isaac book at the end.
Okay.
Okay, but build it in a spreadsheet or in a Word document where you have it really well, and show it to me so I can review it. Okay, but there is a number that I'm expecting at the end, and from experience I know for a building like this, what is a pound per square foot would be. And then you need to also have the columns, but you do not know the size of the columns. So you're gonna have to, again, guess a size and then iterate. And for the preliminary size of the columns, I have a book. Once you know the load per floor, right? And you know the temperature area for each column, you go through that book and it will give you the size of that column. It's quick and dirty, it's 90% correct,
So it's like that, but for the column now. Okay.
right? I mean, I shouldn't teach you this now. Should probably go through the class, you know, with Farhan for the detail analysis, and then there's a lot of shortcut that we have, you know, as a designer that get us to the right answer very quick. So do not use this for
his class.
his class. Okay, this is kind of
That's cheat code.
yeah. All right. Yeah, I think that's good for today. So we discussed the system. We'll be, just to conclude, we're gonna go with post-tension slab, right? With variable thickness based on the span, right? We're gonna have 3 slabs, one at the roof, one at the typical floor for the hotel, and a third one for the subterranean parking. The reason for that is the load are different, and the span more or less are different, but mainly the load, because when you go to the garage, you're dealing with different live load. It's a live load for the cars,
Yeah.
right? Where here, you're dealing with the live load of a hotel building,
Yeah.
right? So that's why you can have 3 different load. We decided that the lateral system will be basically this shear wall, okay? And when I see you next week, I'm gonna have a meeting next week, but I'll try to run. I mean, I push my meeting from today till next week so I can show you this, so you can get started and you have some momentum in the project. But I'll try to, again, either run loose early, or I'll see some of you so I want to review that loading criteria,
Okay.
so you guys can get going with the project. All right?
Is that all you want us to do by next week?
This plus the live load
Okay.
for each.
So final loads of the.
Final load for each floor, and the wind. It would be nice. Now we know site to know the wind, you know, wind criteria and the earthquake.
Okay.
Just an idea, because now you have the dead load for each floor. You can calculate the base shear. So I want you to go to the USGS website and determine the, you know, the acceleration and everything, and an idea about the base shear. Okay. All right. Okay, that's all. Okay, see you guys in class.
See
Bye-bye.
you, Professor.